Titration curves for weak acids and strong bases. When a weak acid is titrated with a strong base, the solution is buffered before the equivalence point and it's basic at the equivalence point. Let's look at a titration that involves acetic acid with NaOH. First part of the problem here. We're reacting acetic acid with NaOH. We're going to form sodium acetate, the salt, plus water. We're going to do start, change, after. So we need moles. So we're going to take the concentration times the volume in liters to get moles. So for acetic acid, 0.0025 moles. For NaOH, 0.001 moles. No salt is present initially. So we have moles. The NaOH is going to be used up. There will be no sodium hydroxide left after the reaction is complete. The change is the same for all species. We cannot disregard the salt now because the salt comes from a strong base and a weak acid, so the salt affects the pH. So I'm going to get the concentration of acetic acid by taking the moles, 0.0015, dividing by the total volume. The total volume is 0.035 liters. So the concentration of acetic acid is 0.043 molar. I also need the concentration of sodium acetate because it affects pH. So the moles, 0.001 divided by the 0.035 liters of solution, 0.029 molar. What I have is a weak acid plus the salt of the weak acid, so I have a buffer solution. And in a buffer solution, when we're doing icebox, we use concentrations. So we have acetic acid reacting with water to form H3O and acetate. Initial change after, 0.043. We solve for the concentration of the acid, H3O is 0, and acetate comes from the sodium acetate, 0.029 molar. Just use X's. We'll set up a Ka expression. Ka is 1.7 times 10 to the negative fifth, and that's equal to X times 0.029. We can use the shortcut, divided by 0.043. X is the concentration of H3O, which comes out to a value of 2.5 times 10 to the negative fifth molar. pH is the negative log of 2.5 10 to the negative fifth, so pH 4.6. So up until we reach the equivalence point, this is a buffer solution. Next problem, same reaction, acetic acid plus NaOH. So write the equation. We'll do start, change, and after again. So we need moles. The moles of acid, 0.0025. The moles of base is also 0.0025 initially. So both the acid and the base are going to be used up. And I will have some salt present at the end of the reaction. I'm going to find the concentration of the salt, sodium acetate. I got 0.0025 moles. Divide by the total volume. The total volume is 50 mils, so 0.05 liters. So the concentration of the salt, 0.05 molar. Now the salt, when put in water, breaks apart into Na+ and acetate ion. Na+ comes from NaOH. NaOH is a strong base, so that means Na+ is weak. Acetate comes from acetic acid, which is a weak acid, so this ion is a strong base, and it will react with water. So we will set up an equation where the acetate ion reacts with water, and that's going to form acetic acid and hydroxide. Now the concentration of the ion comes from the salt, 0.05. Products are 0. Just use the x's for the variables. We need Kb because acetate acts as a base, so Kb is equal to Kw divided by Ka for acetic acid, so 10 to the negative 14th divided by 1.7 times 10 to the negative 5th, and that's going to be 5.9 times 10 to the negative 10th. Set that equal to x squared divided by 0.05. X is the concentration of hydroxide, which comes out to 5.5 times 10 to the negative 6th molar. And then from there I can find the pH. POH is negative log of 5.5 10 to the negative 6th, so POH 5.26. The pH 8.74. So this is a basic solution. So the pH at the equivalence point is greater than 7. As soon as we pass the equivalence point, the pH is solely dependent on the concentration of OH coming from the strong base in NaOH. Weak base, strong acid titrations, we're going to work in just the same way we've done before. However, when solutions of weak acids are titrated with weak bases, the vertical portion of the curve is too short for color indicators to be used. This is the titration curve for the weak acid, strong base, the problems that we just worked. Before the equivalence point, it's buffered. So notice the shape of the curve before the equivalence point. It's buffered right here. If I'm going to use a color indicator, I want an indicator that changes color on the steep portion of the curve. So I would want an indicator that changes color somewhere between, looks like 7 up to a little above 10. I would want a color indicator that changes color somewhere between a pH of 7 to 10.